Okay, class, good afternoon. Today we'll be uh, discussing dynamic analysis in terms of flexural members, which are commonly known as beams. And here I have a definition of what a beam is uh, technically for use in your structural analysis, especially in dynamics. So a beam is defined as a structural member that carries loads transverse to its longitudinal axis such that it produces both rotational and translational displacements. And if we are going to look at the figure here, so we can see two translational displacements which are vertical forces, or they are transverse to the longitudinal axis, and also two rotational displacement which are actually um, located and applied at the ends of the beam. So if we are going to look at the numbering of the degrees of freedom, so you can see here that the DOF numbering, which are represented by what you call the generalized displacement uh, and forces. Okay, so these are generalized displacements and forces. So the term generalized means that they are assumed to be consistent in terms of translational and rotational systems. So for your numbering, so we have here the first DOF constitute your translational displacement at the near end of the beam. Okay, so we have here what you call your I node, and here your J node. Okay, so these are now your near and your far. Okay, of course, from left to right, so this is the assumption of which is your member axis is actually directed going to the right of your longitudinal axis. So there are actually four generalized displacement and four generalized forces that we have to consider. And the first thing we have to take note in this dynamic analysis is, of course, how to compute for your stiffness K. Okay, so the problem is on K value, which you will be using in your differential equation of motion. So remember that our differential equation of motion needs the assembly of your matrix to start doing a dynamic analysis solution. Okay, so for this beam element in general, the differential equation uh, of or for a small transverse displacement of the beam may be given by this moment equation. No? So this is actually your Euler-Bernoulli beam equation, which we have used so many times in our strength of materials and the theory of structures. So where mx, of course, is the equation of the bending moment at any section x of the beam, and u is the transverse displacement, which actually describe the curve upon which your beam will behave. Okay, so this is now your elastic curvature, which is actually connected to your bending moment equation. So for the other relationship that are actually related to this bending moment equation, we can take into consideration the second derivative of your moment to come up with a load equation. Okay, so remember the degree into which your load, shear, and moment diagram are actually related. So we have in your strength of materials definition your y, your theta, your shear, your moment. Okay. Sorry. Y, theta. Okay. Okay, y. Then you have the theta. Then you have the moment. And then you have the shear. And then you have the load. Okay, so these are all interconnected to your differential equation, wherein y is simply equivalent uh, to your elastic curvature in terms of your deflection. Okay, of course here we're not using y value, but rather an u value there. Okay, so we in our strength of materials we often use the variable y to deal with deflection. So if you get dy dx here, you get the slope. Okay, so this is actually your deflection delta. And if you get a d theta dx here, or second derivative of y with respect to x, you get the moment. Okay, so you have the moment equation, and then if you have a dm over dx here, or simply the third derivative of y with respect to x squared, you get the shear. And if you get the derivative of shear with respect to x, you get the fourth derivative of y with respect to x squared, you get the load. That's why here your load equation constitutes your fourth derivative, and so is true with the others. Of course, we still need to add your dimensional property and inertial properties to complete the value of your variable concerned. Okay, so this relationship now are the basis on which your stiffness matrix will be derived later. So take note that the integration of the differential equation of motion above uh, once and twice, not motion, so let's remove the m here. So the differential equation above once and twice will obtain simply the slope and the deflection equation. Okay, so integration of this moment back to once or twice procedure will uh, uh, get you back into the computation of your slope and deflection respectively. And if we are going to continue the solution, of course, the slope equation and the deflection equation can actually be written in this form by simply substituting your u variable in terms of your y variable. Okay, so let's take now the definition of your stiffness Kij, which is simply the force at the nodal coordinate I due to a unit displacement at the nodal coordinate j. So here, the I and j does not mean the near and far ends of your beam here. Your I and j are actually the nodal coordinates. So when you're talking of the a nodal coordinate, you are talking of the degree of freedom. Okay, so the word nodal coordinate means the DOF. Okay, so take note that you are assuming a unit displacement while the other are maintained to be at zero displacement. So if you have here a unit displacement of 1 on translational, the others are fixed, no? So the unit displacement for the here in terms of moment or rotation and the translation is 0, and so with this one is also 0. So what is only assumed to have a value is the coordinate 1, which is simply given by the nodal coordinate in terms of translation. So if you have a beam here, which is a flexible beam, so always take note that okay, always take note that your first coordinate is vertical and your second coordinate is rotational. Okay, so this is also vertical and then okay, rotational. So that's the third and the fourth. Okay, so the I and the j here are the 1, 2, 3, 4 values that are considered. Okay, so your counter is actually from 1 to 4. It's different from the near and far ends of the I and j ends of this beam, which are the nodal coordinate in terms of the endpoints of your beam. Okay, so don't confuse yourself on that. So the beam elements are now shown in terms of their elastic curves due to a unit displacement. So your unit displacement here is 1 translational. Unit displacement is here is also 1 translational, and then the unit displacement here is 1 rotational, and the unit displacement here is actually 1 rotational. Okay, so the arrangement of your displacement will simply change the arrangement of your stiffness matrices. So there's a possibility of putting your nodal coordinate system in a different form. Let's say if I have here your flexible beam, I can number it 1, 2, then 3, 4. Okay, so 1, 2, 3, 4, and that's how this is actually numbered, no? 1, 2, 3, and 4. So basically our program will constitute a numbering such as this to make your stiffness matrix much easier to figure out later. Okay, but the other books uses this numbering, uh, just like this one here. Okay, if we consider now the differential equation of the elastic being arranged in a decreasing order of derivatives, we can set your px load to be 0. So what will happen here is that your ei d fourth dx to the fourth, there's an ei here, but we assume it to be 0, so this can be 0, no? Sorry, this cannot be 0, so what will be 0 is this, the order of derivative. Okay, so we can simply remove the ei in order to simplify the equation. And if this is 0, we integrate it, it becomes c1, and the succeeding integration will yield to these equations here. So you have actually c1x plus c2, then c1x squared over 2 plus c2x plus c3. So the third integration procedure will yield to c1x cubed 2 times 3, 6, c2x squared over 2 plus c3x plus c to the fourth, wherein c1, c2, c3, c4 are constants of integration that can be evaluated using what you call boundary conditions. Okay, so for the first curve n1x above, we make use of the following boundary conditions. Take note that the boundary condition for your first is such that your deflection at x equals 0 is equal to 1 as stated there, or as given, and your slope is also 0 at x equals 0, and at u is equal to L, or sorry, at x equals to L, your deflection is 0, and so with the rotational slope theta, which is 0. Okay, so these are the boundary condition for your first curve n1x, which is actually an approximation of your shape function here. Okay, so something like this. So you can approximate this function as like this one. Okay, wherein the slope here, and the slope here are horizontal, so these are zeros. Of course, the translational displacement there is also 0. Okay, if we substitute boundary condition 1 in equation 4, we get c4 equals 1. And if we substitute boundary condition 2 in equation 3, we get c3 equals 0. So where's that? So these are the equations. Okay, so if we substitute x equals 0 here, these are all 0, so c4, sorry, if we substitute 0 here, this is 1, so this will all be zeros, and c4 becomes 1. And if we substitute at x equals 0, this becomes 0, your c3 becomes 0. So all we need to figure out is what's the value of c1 and c2. Okay, substituting bc4 in equation 3, 0 is equal to c1l squared over 2 plus c2l. we get C2 is equivalent to a negative C1 L over 2, in which C2 can be substituted back to equation 5 to get your C1 value, which will be 12 over L cubed. Okay, so you just simplify this expression and you will yield to a C1 value of 12 over L cubed. And then going back to this equation, C2 can be solved as negative 6 over L squared. And since our coefficients are now complete, we can substitute the C1, C2, C3, and C4 in equation 4 to yield your use of x, which is 2 over x, 2 times x over L cubed minus 3 times x over L squared plus 1. Okay, so remember that this is not the absolute solution for your ux, since we have not included the ei's, so this is only an approximation, which is a function that is needed to approximate the shape of your u. Okay, so ux is actually your n1x, your shape function, which is equivalent to this equation here derived from the procedure. And using the same procedure will yield our values for n2x, n3x, and n4x below. Okay, so you need to take note that for n2x, n3x, and n4x, new boundary conditions must be set. Okay, so boundary condition must be set. So what are those boundary conditions? So you simply look into the curve defined above. So the above functions are known as approximation function or shape functions. Okay, so this is what you call the approximation function or the shape function, because it approximates the shape of your actual solution use of x. Okay, so since n1x is the deflection corresponding to a unit displacement equal to delta 1 equals 1, the displacement resulting from an arbitrary displacement delta 1 is n1x times delta 1, and the total displacement ux at coordinate x due to arbitrary displacement delta 1, delta 2, and delta 3. And delta 4 is simply given by the superposition, of which your use of x now becomes the actual, the real equation of your curve, n1x, a function of x times delta 1, n2x times delta 2, and n3x times delta 3 plus n4x times delta 4, which is a superposition method used in determining your actual solutions. But unfortunately, class, this is not a systematic way of taking care of the solution. So there is a better way of looking into solving the problem on the determination of your displacements or elastic curvature, and that we will be discussing on the next video. Thank you.